Picture this. You're in a totally unfamiliar city, you step out of the subway, completely turned around. You pull out your phone, open Google Maps, and instantly, there it is, that little blue dot showing exactly where you are and which way you're facing. We all use it, right? But almost no one knows the staggering amount of hidden engineering that makes it possible. Welcome to this explainer. Today we're diving into exactly how Google Maps knows where you are.
Now, if you ask most people how this works, they'll probably just shrug and say, it's just GPS, right? Well, actually, no. GPS is not the whole story. If your phone only used raw GPS, your map would be incredibly slow, super jittery, and basically useless indoors. To keep that blue dot glued to your every step, your phone is constantly running a massive invisible tech symphony. So let's peel back the layers of this onion, starting with the absolute foundation. Layer 1 is, of course, the Global Positioning System, or GPS. But here's a wild misconception. GPS doesn't actually track you. Your phone is just a passive listener. It's constantly listening for incredibly precise time pulses sent by synchronized atomic clocks on satellites way up in orbit. By calculating the exact split second it takes for these signals to reach you from at least 4 different satellites at once, your phone uses a mathematical trick called trilateration to pinpoint your exact spot in 3D space.
But to make that math actually work out, we have to talk about speed. Specifically, 299,792,458 meters per second. That's the speed of light, which is literally how fast these satellite radio signals are blasting through space. Because they're moving that fast, if your phone's clock is off by just 1 single nanosecond, boom, your location is thrown off by about 1/3 of a meter. Timing is absolutely everything here. And honestly, that introduces a completely bizarre problem.
Enter Albert Einstein. Seriously, because these satellites are flying around at super high speeds, special relativity means their onboard clocks should tick slower than ours. But wait, general relativity kicks in because they're further away from Earth's gravity, which means they should actually tick faster. It's wild. If engineers didn't account for this temporal tug of war, the entire GPS network would break down in minutes. So they actually have to apply a factory frequency offset to these atomic clocks before they launch, basically making them tick at a slightly different rate down here on Earth, so they sync up perfectly once they hit orbit.
All right, Section 1, Fixing the Urban Canyon.
So, we've got space-age relativity keeping the clocks perfectly timed. But what happens when you bring that incredibly delicate signal down into a concrete jungle? Out in an open field, your phone gets a direct line-of-sight signal from space. Easy. But in an urban canyon surrounded by massive skyscrapers, those direct signals get totally blocked. Instead, the signal bounces off glass and steel before finally hitting your phone. The problem is, your GPS chip assumes the signal traveled in a straight line. Since the bounce took a longer path, your phone thinks you're way further from the satellite than you actually are. That right there is exactly why your blue dot might suddenly teleport to the wrong side of the street, or even a completely different block.
To fix this, modern phones use a seriously ingenious software trick. They tap into massive 3D maps of major cities, the kind built right into Google Earth and Maps. When your phone gets those bounce-delayed signals, it cross-references the data against its internal 3D model of the skyscrapers around you. It mathematically untangles those reflection paths on the fly and snaps your blue dot right back onto the correct sidewalk.
But even with perfect timing and smart 3D maps, raw GPS has a massive, glaring bottleneck. Every GPS device has to download orbital data, stuff called ephemeris and almanac data, just to know where the satellites actually are. If you try to pull this directly from a satellite, it trickles down at a painfully sluggish 50 bits per second. If your phone is starting cold, that download can take up to 12.5 agonizing minutes. And let's be real, you're not going to stand on a street corner for 12 minutes just waiting for a map to load.
And that brings us to the next layer of our tech onion, assisted GNSS, usually just called AGPS. Instead of waiting on that agonizingly slow satellite download, your cell carrier sets up dedicated cache servers. These servers are constantly downloading the orbital data from space. So, the second you open Google Maps, your phone totally bypasses the slow satellite link and just instantly grabs the data over your high-speed cell or Wi-Fi network. It essentially warms up your GPS receiver, shrinking a 12-minute wait down to mere seconds.
Moving on to Section 2, Wi-Fi's Secret Indoor Radar.
Okay, so what happens when you walk deep inside a sprawling megamall or a giant airport terminal, and you completely lose both GPS and cell service? How on earth does the blue dot keep tracking you indoors? Well, enter the IEEE 802.11mc protocol, commercially known as Wi-Fi Location or Fine Timing Measurement, FTM for short. Now, this isn't just your phone guessing based on how strong a Wi-Fi signal is, because signal strength gets totally messed up by walls or even just crowds of people. Instead, FTM acts like an active indoor timing radar. It actually measures the round-trip time of a signal traveling back and forth between your phone and a nearby Wi-Fi router.
It's a really elegant little handshake. First, your phone pings a request to the router. Then, the two devices exchange these rapid bursts of data frames. Your phone records the exact nanosecond timestamps of when it sent and received them. By taking that round-trip time and cutting it exactly in half, the phone calculates the precise time of flight. And the absolute genius part of this, because it's measuring a round trip, your phone's clock and the router's clock don't even need to be perfectly synced up with each other.
Once your phone figures out its exact distance from a single Wi-Fi router, it just rinses and repeats. By pinging 3 or more nearby routers and grabbing their timing data, the phone uses trilateration. Yep, the exact same math used by those multi-million-dollar space satellites to pinpoint your exact location anywhere inside the building.
And this specific tech is evolving incredibly fast. The base 802.11MC standard gave us about 1 to 2 meters of accuracy indoors. The newer 802.11AZ amendment pushes that under a single meter by using multiple antennas and keeping things private with passive ranging. But the upcoming 802.11BK standard, it uses massive 320 megahertz channels and promises to track a device indoors down to less than 10 centimeters. We're talking pinpoint precision.
Which brings us to Section 3, Dead Reckoning in the Dark. Now, imagine you're walking deep underground in a subway tunnel. No GPS, zero cell service, absolutely no Wi-Fi, just total signal darkness. Yet, amazingly, Google Maps keeps moving your blue dot right along the tunnel on your screen. How is that even possible? The answer is Pedestrian Dead Reckoning, or PDR. This is a fully autonomous inertial navigation system. It's actually borrowed straight from aerospace technology, and it relies purely on the physics of your body's movement, reading the microscopic sensors physically built right into your phone's hardware. The first crucial sensor here is the gyroscope. It continuously tracks your heading, specifically your yaw angle. Without needing a single outside signal, your phone can literally feel exactly when you turn a corner in that dark tunnel, mapping your changes in direction perfectly. Next up is the accelerometer, which basically acts as a highly advanced pedometer. But it doesn't just lazily count your steps. It uses really complex algorithms to constantly analyze the physics of your walking motion, calculating the exact length of every single step you take in real time.
Then, your phone does something called sensor fusion. It grabs your very last known GPS or Wi-Fi coordinate from right before you entered the tunnel and seamlessly stitches it together with the continuous feed of heading data from the gyroscope and the step length data from the accelerometer. By fusing all this sensory data together, it basically draws your ongoing trajectory in the dark, keeping that blue dot moving in perfect sync with your actual footsteps.
And finally, Section 4, bringing it all together.
Whenever you glance down at Google Maps, your phone is actually cycling through this incredible hierarchy of systems in mere milliseconds. Think about it. It's constantly prioritizing and blending data from atomic clocks, factoring in Einstein's relativity, cross-referencing 3D skyscraper maps, leaning on cell networks for rapid data caching, bouncing nanosecond Wi-Fi radar pulses indoors, and when all else fails, defaulting to inertial aerospace sensors. All of that happening constantly in the background.
Honestly, it's so easy to take it for granted. It feels like magic, right? But the reality is that the little blue dot is driven by one of the most complex, multi-layered ecosystems of mathematics, hardware, and software ever created, all collaborating seamlessly just to figure out exactly where you're standing on the surface of the Earth.
And that is really the main takeaway from this explainer. The next time you open up Google Maps, I want you to take just a second to appreciate the sheer, unbelievable scale of the engineering making that tiny dot possible. You're not just looking at a simple GPS chip, you are holding a globally synchronized orchestra right in the palm of your hand.
Which leaves us with one final, kind of provocative thought. If your phone goes through all of this immense, invisible mathematical effort multiple times a second simply to pinpoint your location, what else is it silently calculating right now? Thanks for joining me on this explainer, and keep questioning the incredible tech hidden right in your pocket.